Well, my dear students, this is third lecture in the series of sheet metal forming we are going to discuss. If you remember the earlier lectures where we started with the basic of sheet metal forming, different methods, different operations, the machines and equipments, toolings required for sheet forming, we started with, you have already seen it. In this lecture we are going to discuss especially the deep drying operation and then subsequently redrying operation and design aspect for your different aspects of FLD diagrams you discuss, right. So, recall back all the previous lectures. One has to be very careful, say when we start with the sheet material, especially the material that is the metal, you know, when the forming takes place, if you recall, we mentioned the limit to the forming as diffused necking, and also we mentioned the localized necking, right. So, if you recall, in the diffused necking that puts a limit to forming, especially sheet forming in biaxial tension. The necking which occurs in the uniaxial tension is in fact inhibited, you remember, if sigma 2 by sigma 1 is more than half, right, and the materials then develops diffuse necking, not, it may not be visible in fact, right. So, if the sigma 2 by sigma 1 is greater than half, the material is going to develop diffuse necking, right. The limit of uniform deformation in strip loading especially occur at a strain which is equal to the strain hardening exponent, which is equal to n, right. So, that you recall it at, and when we consider the localized necking, that is the case. If you see this figure, the localized necking where the plastic instability of a thin sheet will occur in the form of a narrow localized neck as shown here, like dotted lines, and that is followed by fracture of the sheet. Okay. So, normal strain along x must be 0, that is a necessary thing, and if you remember here in the diffuse necking, your the strain hardening component becomes equal to the limit of the uniform deformation, but in localized necking we have 2 times of the strain hardening, okay, and that is how the normal strain along x2 must be 0. X2 direction has been shown there, if you see there, okay. So, this shows in a strip. As far as the deep drying now it concerned, deep drying because there is a necking happens, and we concern initially that the material is isotropic material basically, but it never happens, there is always some kind of anisotropy. So let us start with deep drying. You know, all of you might have seen different utensils, bowls, cups and all those things in your houses as household applications. So have you ever thought of how these components are made? Because it is no doubt it is made of sheet metals, and especially the stainless steel sheets are very common in these. So these components as shown here, if you see the shallow drying, if you see the bowls, if you see the cups, etc., it comes into category of deep drying operation, right. So the deep drying is a the metal working process which is used for shaping flat sheets into cup shaped articles, right. Cup shape may be anything, shallow cup, deep cup, etc. So for an example, if you take bathtubs, bathtub is also an example, cell cases, automobile panels, all these examples falls into this category of deep drying. Okay. So what happens in deep drying? If you see the basic, if you look at the before drying what happens and after drying what happens. So in usual case, in deep drying of a cylindrical cup say, so you have a punch, you have a die, you have a blank holding, and you have a proper spacing the clearance between the die and punch. So what happens, the before drying you the pressing the you require to be the sheet metal is required to be pressing the metal blank of appropriate size into shaped die with a punch as shown here. See, so the before drying what happens, sheet is kept, the punch is ready, the blank holding is there and die is there. So you apply a pressure P, the blank holding diameter is D, the radius of the blank holder corner is given, that is a very important issue of design, thickness of the sheet is say T. So after drying you can see how the punch goes and the whole sheet goes inside and takes the form of the die. So that is a very simple deep drying operation. So what happens? So if you look at this figure, it is the base done with double acting press. So you require a press which is double acting for these operations. So you can also, it can be done using a blank holder or a hold down ring as well, as because you have to apply a blank holding, otherwise wrinkling and other defects comes into picture. In fact, the hold down ring is also used and the blank holder can also be used. But what happens, there is a complex interaction between metal and die depending on the geometry, okay, and almost there is no precise mathematical description about this. There is no precise mathematical description used to represent the processes in simple terms in fact. So you see after closure the second stage and third stage where the hold down ring is used and then it comes to be the drawn. So what happens if you analyze the whole process, that is a cup which is subjected to three dimensional or three different types of deformation. If you look at this figure, so as the metal is being drawn into the die with the help of punch, there is a very complex and usually three different types of deformation happens. So as the metal is being drawn, there is a change in radius and there is an increase in cup wall. thickness as well as, right. So if you look at in the beginning and then you see the second one, the middle one where it is about to go, and then if you look at a portion of the seat which is being drawn, which is shown there on the top, you have three major portions, which is called, the top one is called as the flange, right, and then the other, the cup wall, and then the punch region, right, and you have see the top flange is under triaxial loading, whereas the cup wall portion has a biaxial loading, and similarly the punch region, which is at the bottom almost, is also a biaxial loading. So if you look at, say, the stresses and deformation in a section from a drawn cup, which is shown here, right, and on the right side you can see the thickness profile of the drawn cup. So thickness at the top is more, then it decreases, at the near corner it is almost minimum, and then the bottom region is almost constant. So it may not be a good design. In fact, the thickness must be almost equal. So to give this, the clearance between the punch and the die is very important. Usually the clearance between the punch and die must be greater than 10 to 20% thickness of the seat. So what happens, the metal in the punch region, if you see here, okay, is thinned down, and because of the biaxial tensile stresses, and metal in the cup wall region is subjected to a circumferential strain as shown here, or hoop, and a radial tensile strain. The metal at the flange region is bent and straightened as well as subjected to a tensile stress at the same time, okay, and that is how you look at it is at the flange region, it is triaxial stresses acting, right. So that is the basic thing which happens in any kind of deep drawing operation. There is another term we call as redrawing. Redrawing means you draw once and then take it to the another die and again redraw, or in the same die you redraw again and again. So redrawing is a term used to successive drawing operations by reducing a cup or drawn part to a smaller diameter, right, and increased height, and this is what is called as redrawing, okay. If you look at the examples of redrawing, if you see, so you have a slender cup such as cartridge case and the close in tubes, like you look at the figure A, B and C, that is how the first draw, and then it is taken to the another set of the die, second draw, and then it is again taken to the, so you get a different type of shape that you can provide, okay. So if you compare the direct or regular redrawing, there are two types of redrawing in fact. One we call as direct or regular redrawing, and the second one we call it is the reverse or indirect redrawing. So what happens in direct redrawing, which is a smaller diameter is produced there by means of a hold down ring. The metal must be bent at the punch and unbent at the die radii, okay. You can see the figure A, which is a kind of taper die that allows the lower punch load, okay, that is how it is shown. In figure B, which is the case where the reverse or indirect redrawing, here the cup is again turned inside out, the outside surface becomes the inside surface, and in C there is a better control of wrinkling and there is no geometrical limitations to the use of a hold down ring, okay. And that is how we have the three different cases of redrawing, okay. So that gives you how the different varieties of redrawing can be obtained by different combination of direct and reverse redrawings, okay. So as far as the punch force is another very important issue, because it is the punch which directs the complete force, and so there is the at what stroke it has to provide, that is also important. So if we look at the punch versus punch stroke, the punch force is in fact given by a combination of three forces, which is first, which is called as the deformation force, second is called as the frictional force, and third we call it as the ironing force. So the punch force can be equal, can be said as the equal to the force of deformation plus force of frictional plus force of ironing. So deformation force varies with length of the travel, right, and the frictional force mainly from hold down pressure it happens, okay. And after the cup has reached the maximum thickness, then it comes to the ironing force. So the ironing force after the cup has reached the maximum thickness, it comes, so part of that, and that is how the total punch is sum of these three forces, alright. So one has to be very careful, and one can think of how to reduce the frictional force, how to reduce the ironing force. Deformation force you cannot reduce, no doubt, but other two can be reduced, right. So now look at the dryability, because any sheet, if it is very hard or it is very tough, it would be very difficult to draw. So we consider a term, or we say rather let us see the dryability. What do you mean by dryability? And particularly in deep drying, the dryability is a term which concern, or which is a ratio of the initial blank diameter, say D0, to the diameter of the cup which is being drawn from the blank punch diameter dp, if dp is the punch diameter. So that is the ratio of the two dryability. So and then there is a term which called as the LDR ratio, that is the limiting draw ratio. So limiting draw ratio is defined almost equal to the D0 by dp maximum, okay, and that is almost equal to the e raised to the power n, or the strain, engineering strain raised to the power n, where n is the efficiency term according to the frictional losses. It is not exactly n, it nu, we may call it as a nu. So nu is a efficiency term according to the frictional losses. Normally the average maximum reduction in deep drying is generally 50%. If you see, average maximum reduction in deep drying is generally 50%. So if you look at the dryability, there are certain practical considerations that affect dryability, okay. Like you have dye radius, so that affects the dryability is one, the dye radius. So the dye radius should be about 10 times the sheet thickness, okay, and the punch radius similarly, it is a sharp radius in fact, that leads to local thinning and tearing, So, the clearance between the punch and the die should be about 20 to 40%, and that should be greater than the thick. So, around 20 to 40% greater than the thickness, sheet thickness should be there, and the clearance should be such. As far as the other consideration for dryability is the hold down pressure. So, and this hold down pressure is around 2% of the average shear stress, that is the sigma 0 and sigma u ultimate strength. The hold down pressure is around 2% of the average of sigma 0 and sigma u. And to reduce the friction we may use lubrication. So, lubrication of the die side to reduce the friction is also very important. And as far as the material properties is concerned, we must look at the low yield stress material having high work hardening rates and high value of strain ratio of width to thickness capital R must also be chosen, because since the forming load is carried by the side wall of the cup, failure therefore occurs at the thinnest part, right, as it is shown here. So, you see the failure happens to be either at the top of the flange or at the bottom near. So, because the forming load is carried by the side wall of the cup, and that is how the failure mostly occur at the thinnest part, because the thinnest part near the flange or at the bottom side it happens. And in practice the material always fails either at number 1 the shoulder of the die as shown, and secondly the shoulder of the punch as shown, right. So, that is the chances. So, to avoid the failure one has to take care of these practical consideration concerning the die radius, concerning the punch radius, right, concerning the hold down pressure and proper lubrication and a proper material. Okay. So, for apart from that, there are certain practical considerations for round and rectangular cells also. Okay. So, rectangular cells are slightly different. It may be rectangular symmetric cell, it may be a kind of a square cell as well. So, because you require different pressure, because in the form of tension, compression, friction, bending, etc. So, the different pressures force the material into shape, because into depending on the rectangular or round, and perhaps with multiple successive operations are required in these cases. So, look at the round cell here, in one case where, so you require a different pressure in the form of tension, compression, friction, bending, etc. If you look at the right side where you have a rectangular cell, so that is the another situation where you have a different flow pattern at sides and corners like here, because the corner requires similar flow as round cells, while the sides need simple bending, right. The corner radii controls the maximum draw depth, as I said. The center of center to center distance of corner is in fact it should be greater than or equal to the 6 times of the corner radii, and bottom radii must be greater than or equal to the corner radii. That is how one has to be careful there, because as I said, the dryability is very important issue, and to avoid any kind of fracture either at the flange side or at the bottom side, a proper test must be carried out, and that can also be used to improve the dryability. So, to avoid failure in the thin part, that is at the punch or flange region, metal in that part need to be strengthened, right, or the weaken the metal in other parts, to that means to correct the weakest link, right. So if the sufficient friction is generated between the punch and the workpiece, more of the forming load is carried out by the thicker part, right. So one can concern about the crystallographic texture, that is the slip system, and one can also concern the degree of anisotropy or the strain ratio, capital R ratio. Okay. So these two things one can consider to control these things. If you look at this figure where the strain hardening component is along the x axis and another you have the draw ratio is drawn at a different uh, R ratio. So you will see that the regions where R is starting from 0.5 to 1 and it goes up to 2, right. So you can see the failure at the punch radius in the region bottom, and if it is the draw ratio is more than that, that is above 2.0, then also there is a failure at the die entrance. So this kind of plot helps you to locate the safe region which is shown there. Okay. So all kind of tests are required. So and with these implications, the one can improve the drivability and one can reduce the failures at these two regions. In fact, the plastic strain ratio, right, the plastic strain ratio capital R is a measure and that measures the normal anisotropy, which denotes high resistance to thinning in thickness direction. Okay. So that is simply given as this equation ln Wa by W and ln H0 by H, where W0 and W are the initial and final width, and H0 and H are the initial and the final thickness, if you see. But it is very difficult to measure the thickness on the thin sheet while the forming takes place. Therefore, we use this formula capital R as this one here, that is ln W0 by W divided by ln WL divided by W0 L0. Okay. And let us see what happens, and let us take one example. So this example where a tensile test is carried out on a special deep drying steel, and it shows a around 30% elongation in length and around 16% decrease in width. Okay. So let us find what is the limiting draw ratio that would be expected for the sheet. Okay. So how can we proceed, because it is already given that it is 30% elongation in length and 16% decrease in width. So that means 13% elongation in length means L minus L0 by L0 is 0.30. Okay. And 16% decrease in width means W minus W0 by W minus W0 divided by W0 is 0.16. So one can find out this, that is L by L0 is 0.1.30, and similarly W by W0 becomes to be 0.84. So one can then find out the R, that is the ratio. If you use the previous equation as I said, so if you substitute, the R comes out to be 1.98, right. So this is an example already taken from the Dieter page number 6 73. So one can refer this case, right. So that's how says the application of the plastic strain ratio capital R, and this plastic capital ratio, as I said, uh, the forming load, uh, one can reduce the thicker part, and uh, especially when you come to the crystallographic texture, slip, and the degree R, the strain ratio, as I said. So another very important issue is your forming limit criteria, because anything that you are going to produce, anything you are going to draw, it should be defect free. There should not be any defects. So usually when we form deep drawing operations, we perform forming limit criteria. So that's a tensile test. So by tensile test only provides the ductility, work hardening, but it is a universal test, tension test with frictionless condition, okay, under forming limit criteria, which cannot truly represent the material behavior obtained from unequal biaxial stretching concerning in sheet metal forming, as I said. So tensile test is not sufficient for sheet, and therefore the sheet metal formability test is required, and these tests are designed to measure the ductility of a materials under condition which is very similar to those which is found in sheet metal forming, okay. And so there is a one such popular method, we call it is as erection cupping test, okay. So erection cupping test, if you look at here, the test is very simple and easy, and generally it is for symmetrical and equal biaxial stretching is performed, and that allows the effects of tool workpiece interaction and lubrication on formability to be studied. Okay. The sheet metal specimen is hydraulically punched with a 20 mm diameter. So you can see the ball. So the sheet metal specimen, that is the blue is the specimen, is hydraulically punched, right, like here, with a 20 mm diameter ball. A small ball is also visible, a steel ball at a constant load of around 1000 kg, right. So you can see the result of the cupping test on the sheet, steel sheet, as shown there. So the distance d is measured in millimeters, and it is known as Erection number, is called as Erection number. So you can measure the diameter d. The forming limit diagram, now it is one can see here. So before deformation these rings, and you can see the after deformation the rings, and the sheet is therefore marked with a close packed array of circles using chemical etching or photo printing techniques, and that's how the grid analysis uh, before and after deformation in the sheet. The blank is then is stretched, as I said, over a punch, resulting in a stretching of the circles into the ellipse like there on the right side, and the major and the minor axis of an ellipse represents the two principal strain directions, therefore in the stamping, okay. The percentage changes in these strains are compared in the diagram which is shown here. You can see that's how the forming limit diagram, the major, the minor strain on the x side, and the the failure or the major strain on the y side is drawn based on the measurements of the major and minor axis, and the comparison is done in a given thickness of the sheet. Here you can see the failure, the safe region and the failure region is then marked out of this. You can see the below the line AB it is a safe, and above that it is a failure, and that is a kind of steel is chosen. Let us take one example to explain it. How do we go draw it, and how do we draw the diagram, the forming limit diagram. So let us take this example where a grid of 2.5 mm circle is electro etched on a blank of sheet steel, and after forming into a complex shape, the circle in the region of critical strain is distorted into and ellipse with major diameter of around 4.5 mm and the minor diameter as 2 mm is obtained. Okay. Then how close is the part to filling in this critical region? How can one study how to draw it? So out of the data available, see, one can find out the major strain. So what is the major strain? So major strain, because the major diameter is 4.5, okay, and the minor diameter it is initially is 2.5, okay, with a minor diameter as 2 mm. So the major diameter will be what? That is the E1, one can. So 4.5 minus 2.5 divided by 2.5, and that gives 80%. And similarly the minor strain, because the minor diameter is 2, so 2 minus 2.5 divided by 2 that gives as the minus 20%. Okay. So if you look at these situations, so the coordinates indicate that the part is in imminent danger of the failure, you can see, because if you see the red part, it is the major, it is 80 and it is on the minus side as 20, so it is marked the circle as 20. So this shows that this indicates the part is in very imminent danger of the failure region. Okay, and that is how one can locate the different circles and at the different regions, and one can locate the, say, the path of the limit diagram. So that gives the path. So out of the path you can choose the safer region and unsafer region. So safer region you can, and corresponding safe region you can find out the major strain and minor strain, and that is how it shows you, it guides you that to avoid the failure. Okay. So this is what the very basic. As I said that the purpose of these formed parts, especially the sheet forming deep drawing, there's the limit this diagram puts you is the limit that there should not be any defect. So the defects in formed part, if you look at this sheet, this figure, it's a very strained one part, the another is a good part, another is a better part, and it is a very cleaned edge, that's how. So here one can look at the edge condition for the blanking operation, if you take for example. So that's how the defects concerning to the blanking operation, the 4 cases, it is very strained, very good, better, and a very clean edge. So what you require? You require a very clean edge, right? So once you form, as I said, the deep drawing, the local necking or thinning or buckling and wrinkling in different regions of the compressive stress is very important to consider. And also the, as discussed earlier also, that the spring back tolerance problems comes. So the spring back tolerances are to be properly selected, and the crack near the punch region in deep drawing, in fact it can be minimized by increasing the punch radius and lowering the punch load. So that's the one aspect. So defect has to be reduced near the punch region. In fact, the radial crack is another defect in the flange and edges of the cup due to not sufficient ductility to withstand large circumferential shrinking uh, load. Okay. So that's the radial crack happens. Another defect we call it the wrinkling, very common defect of the flange are the edges of the cup resulting from buckling of the seat, which is due to circumferential compressive stresses, and this can be solved by using sufficient hold down pressure to suppress the buckling. Okay. Usually the surface, another defect we call it the surface blemishes, which is due to the large surface area. For an example, orange peeling, especially in large grain sized metals, because each grain tends to deform independently, and that is how the orange peeling happens, and therefore one must use fine grained metals to avoid the orange peeling. Another defect is mechanical fibering, and has little effect on formability. In fact, the crystallography fibering or preferred orientation may have a large effect of the defects. Like for an example, when the bend line is parallel to the rolling direction, especially, or earring in deep drawing cup due to anisotropy properties happens like this. Here the earring in the deep drawn, so there is a kind of hold up on the sides, and that's how, because of uh, the bend line is parallel to the rolling direction, then this happens. This is what shows the stretch strain in low carbon seat after drying. So this kind of defect, which is called as the stretcher strain or worms, right, and this is in fact a flame like pattern of depressions, and this is associated with yield point elongation, right. The metal in the stretcher strains has been strained an amount around B, capital B, while the remaining received essentially around 0 strain. Okay. The elongation of the part is given by some intermediate strain capital A, as the number of stretcher strain increases during deformation. The strain will increase until the entire part is covered in it, and has a strain which is equal to capital B. So the A and B has been marked here, the point A. Okay. So the stretcher strain, where the strain which is equal to the point B equal to, if you look at the relation of the stretcher strain to the stress strain curve, which is shown here, and that's how the things. So the elongation of the part is given by some intermediate strain A there. So, the number of such stretcher strain increases during the deformation. The strain will increase until when the entire part is covered with it and has a strain which is equal to corresponding to B. Alright. So, these are the some of the defects. Usually one can avoid taking certain precautions as I discussed, and there are few more topics in the seat forming we would continue further, but for your information these are some of the references one can use. The Dieter book, which is very important book, GE Dieter, that is a mechanical metallurgy, one can follow this. The other book, which is the Edward Enders Manufacturing with Materials book, and the other books you may use some kind of reference book as well as, and as far as the varieties of operations are concerned we will discuss later. So once again I would like to thank you all for keeping patience, so much patience, and listening carefully. But please do not forget to give your feedback about this lecture. So I thank you once again, all of you. Thank you very much.